Assalamualaikum and good afternoon. I am Nur Habzan binti Bariman from Polytechnic Muazzam Shah, Pahang. Today I want to present laser cladding process to enhance surface properties of hot press forming die. To start, let me brief about the content of this presentation. First, introduction, then die defect, repairing option, laser cladding, and last, conclusion. Technology of metal forming rapidly developed in recent years. It became one of most important technology in tooling industry. In metal forming, blank material deformed to take shape the die geometry. Now it recognized as a top technology in automotive manufacturing sector. It produces ultra-high strength component of automobile structure with strength up to 1500 megapascal as shown in figure. In recent, Proton Malaysia use hot press forming technique to improve safety element when car crash. Die is one part in hot stamping component. When in use, die are exposed to surf condition, regular wear, impact, corrosion, thermal cycling, and high stress cause retrotation to the die. Figure show type of defect in die and mold. The defects are dent and digging, plastic deformation, aid deterioration, wear, crack, and heat check. Die wear and failure significantly affect the service life of die, resulting in the need for a new die, which is usually expensive and unexpected high production cost. Figure show option method to improve or repairing defect in die and mold. The method is gas tungsten arch welding, electron beam welding, plasma transfer arch welding, cool spray method, laser based deposition, electro spark method, and thermal spraying. But this topic just focus on laser based deposition method. The laser technique is laser cladding. One of the techniques to modify or improve surface properties in advanced manufacturing is laser cladding process. The advantage of implement laser cladding are improved grain size, increased hardness, minimal dilution, and produce new surface properties. Laser cladding used as a laser heat source to produce the desired clad layer during laser processing. The deposit material can be transferred to the substrate by several methods as shown in figure A, B, C, and D. Figure A shows pre-placed powder method, B, paste powder on the substrate, C, powder injection, and D, wire feeding for laser cladding technique. Laser cladding with powder injection is proven to be the most effective method to produce clad layer. During cladding process, the laser beam melts the powder particle and produce thin layer on the substrate. Figure show laser cladding process. A very thin powder layer has to be melted for the substrate to achieve metallurgical bonding with minimal dilution. The cladding process starts with heat transfer of the liquid coating to the substrate. At this point, the coating begins to solidify. Energy from the partially solidified coating and the laser continues to partially melt the substrate and provide a metallurgical bond between the coating and surface. Then, result properties were characterized from surface topography, hardness, subsurface microstructure, and residual stress. Dilution is to determine clad quality. Dilution defined as the ratio of the clad depth in the substrate over the total clad height. The dilution rate should be suitable 10 to 25%. Dilution increase with increase in laser power and decrease with increasing scanning speed. Dilution and molten depth of substrate increase with the rise of laser power. The depth of matte layer must be as small as possible to produce homogeneous microstructure and good metallurgical bonding, and coating free from pores and crack. Basically, 3 regions were produced in subsurface material after cladding process. First, clad layer. Second, heat affected zone or partially melt zone. And the third layer is substrate. 3 region formation in clad layer was due to beam interaction time and laser power. For example, figure A shows percent of particle in clad layer was due to incomplete melting on the nickel titanium particle within the rapid residence time. In the upper region, X and Y of figure B, incomplete melting of nickel and titanium particle was due to different melting point of nickel, titanium and steel substrate. Grain structure observed in region Z were formed as a result of lower solidification rate relative to region X and Y. When the heating hit, a small percentage of nickel titanium particle melt in the substrate and was pushed to region by high irradiant laser beam at region Z. As the laser energy penetrates deeper into the sample depth, the cladding surface solidifies at lower cooling rate. Thus, grain refinement appears in region Z and varies as a result of the heating and cooling rate at different laser parameter settings. Overlap laser spot in the sample cause additional heating of the clad layer which delayed the solidification. In laser surface modification, rapid localized heating and cooling produce smaller grain size and initiate phase transformation. Laser power affected the clad layer width and depth formation on the substrate. Figure show cross-section of clad layer at different laser pulse energy. A 6 joule, B 10 joule, C 20 joule, and D 30 joule. At laser pulse energy 6 joule, laser clad layer was discontinuous with large pores. While for laser pulse energy at 10 and 20 joule, the layer much more dense. And last, at higher pulse energy at 30 joule, complete melting and eliminate of shrinkage porosity, produce good metallurgical bonding. Figure show reduction of micro-hardness of clad matrix with increasing depth. From the figure, clad area have a high hardness. Hardness increased due to grain refinement with martensite transformation. Hardness from the top surface of the coating show a moderate decreasing trend. Hardness value at the top of the substrate layer increase cause of localized metallurgical change with existence of an element transition zone. Then hardness rapid drop through the heat affected zone and constant drop. Hardness lower in the substrate due to depth of coating reduced hardness in the substrate. This trend produces metallurgical bonding between coating and substrate. And the conclusion, using suitable parameter produce hard layer with excellent metallurgical bonding to the substrate material and uniform composition and preferable coating thickness. To enhance surface integrity of the material, the above factors should be emphasized. Thank you.